In this video, we'll cover a range of important reactions involving alcohols in organic chemistry. We'll discuss methods to convert primary alcohols into primary halides using concentrated hydrohalic acids, methods to improve leaving group ability by converting alcohols into tosylates, and methods to produce alkyl halides from alcohols without forming carbocation intermediates by using reagents like SOCl₂ with pyridine, PBr₃, and pi3. Additionally, we'll explore ether synthesis, including the Williamson ether synthesis via the SN1 mechanism, and acid-catalyzed ether formation, highlighting their utility with alcohols. Finally, we'll cover the acid-catalyzed cleavage of ethers to regenerate alcohols. Let's start off with a quick review. As we've seen many times before, the hydroxyl group in alcohols is naturally a poor leaving group. To address this, protonating the alcohol transforms it into an oxonium ion, converting the hydroxyl group into its conjugate acid and significantly enhancing its leaving group ability. This modification enables the alcohol to participate in SN1 and E1 reactions, and less commonly in SN2 and E2 reactions. To convert primary alcohols into primary halides, concentrated HBr or HI can be used. These acids protonate the hydroxyl group of the alcohol, forming an oxonium ion that serves as a better leaving group. This oxonium ion is then displaced via an SN2 reaction with the halide anion acting as the nucleophile. This method is effective for HBr and HI as bromide and iodide ions are sufficiently strong nucleophiles for this process. However, it is less effective with HCl because chloride is generally too weak a nucleophile for the reaction to proceed efficiently. To convert secondary and tertiary alcohols into halides, we can employ this method by reacting the alcohols with hydrohalic acids, such as HCl, HBr, or HI. Protonation of the hydroxyl group by these strong acids forms an oxonium ion, which is an excellent leaving group. This ion then departs from the substrate, forming a carbocation intermediate that can participate in SN1 or E1 reactions, as previously discussed. The formation of the carbocation intermediate makes it susceptible to possible rearrangements. For example, consider a secondary alcohol that would be intended to produce a secondary halide via a secondary carbocation. However, this carbocation will rapidly rearrange into a more stable tertiary carbocation, ultimately yielding the tertiary halide instead. Additionally, the formation of a carbocation intermediate can result in competition between substitution, SN1, and elimination, E1 reactions, often yielding a mixture of products. However, under specific conditions, one pathway may dominate. For example, when a secondary alcohol is treated with a strong acid like sulfuric acid, H2SO4, at high temperature, elimination is favored. In this case, the secondary carbocation intermediate undergoes rearrangement to a more stable tertiary carbocation, which then proceeds via E1 elimination to form an alkene as the sole product. To synthesize halides from alcohols while avoiding rearrangements, we can use methods that proceed via the SN2 mechanism. One effective approach involves first converting the alcohol to a tosylate. This is achieved by reacting the alcohol with tosyl₂ in the presence of pyridine, forming a tosylate ester while retaining the configuration of the original alcohol. Because the oxygen atom of the alcohol attacks the sulfur of the tosyl₂, no inversion of stereochemistry occurs at this step. Tosylates are excellent leaving groups due to the low pKa of their conjugate acid, around -3, making them highly effective for subsequent SN2 or E2 reactions, depending on the substrate and conditions. To obtain a halide, the tosylate can be treated with halide salts, such as lithium chloride, sodium bromide, or potassium iodide, in a polar aprotic solvent like dimethyl sulfoxide, DMSO. In this setup, methyl primary and secondary substrates undergo substitution via an SN2 mechanism. Because the tosylate serves as the leaving group in the SN2 reaction, the reaction leads to an inversion of configuration as the halide product forms. There are also reagents we can use to convert primary and secondary alcohols directly to halides, such as chloride, bromide, and iodide. The first reaction converts primary or secondary alcohols into chlorides using thionyl chloride, SOCl₂, in the presence of pyridine. In this reaction, pyridine acts as a base, deprotonating the alcohol and forming an alkoxide. This alkoxide then attacks the electrophilic sulfur atom in thionyl chloride, resulting in the formation of an ester linkage between the oxygen of the alkoxide and sulfur, while one chloride ion is released as a leaving group. This released chloride ion then acts as a nucleophile, attacking the carbon attached to the thioester in an SN2 mechanism, breaking the carbon-oxygen bond and leading to the formation of a sulfur-oxygen double bond. The final products are the alkyl chloride, sulfur dioxide SO2, and pyridinium chloride. The second reaction converts primary or secondary alcohols into bromides using phosphorus tribromide, PBr₃. In this reaction, the hydroxyl group of the alcohol attacks the electrophilic phosphorus atom of PBr₃, displacing one bromide ion as a leaving group. Phosphorus tribromide can react with up to 3 alcohol molecules, leading to the formation of a trialkyl phosphite intermediate. Each alkoxy group in this intermediate is a good leaving group, which allows for the SN2 substitution reaction when attacked by a bromide ion. This substitution yields the corresponding alkyl bromide. The final products are 3 molecules of alkyl bromide and 1 molecule of phosphorus acid, H3PO3. This reaction also works with phosphorus triiodide, which would give the alkyl iodide product rather than the alkyl bromide. All 3 of these reactions proceed via SN2 mechanisms, which avoid the formation of carbocations and consequently eliminate the risk of carbocation rearrangements. Additionally, because these reactions follow an SN2 pathway, there is an inversion of configuration from the starting alcohol to the halide product. These halides can participate in a variety of reactions we've covered in previous videos. Now that we've discussed methods to convert alcohols into good leaving groups and halides, let's turn to the reactions involved in ether synthesis. As we've discussed, the hydroxyl group of an alcohol is weakly basic and weakly nucleophilic. However, when treated with a strong base to deprotonate the acidic hydrogen, the alcohol forms an alkoxide ion, which is a much stronger base and a better nucleophile. These alkoxides are excellent nucleophiles for SN2 reactions and serve as effective bulky bases for E2 reactions. We can synthesize ethers by taking advantage of alkoxides as strong nucleophiles in the Williamson ether synthesis. In this reaction, an alkoxide salt is prepared by treating an alcohol with a strong base, such as sodium hydride, producing the sodium alkoxide salt and releasing hydrogen gas as a byproduct. The resulting alkoxide salt is then reacted with an alkyl halide in an alcoholic solvent, typically the conjugate acid of the alkoxide, to undergo an SN2 mechanism, forming the ether. Because this is an SN2 reaction, it works best for primary and methyl alkyl halides. Secondary and tertiary alkyl halides will often give E2 elimination products due to the strong basicity of alkoxides. Intramolecular Williamson ether reactions are also possible. If a molecule contains both an alcohol functional group and a good leaving group, deprotonation by sodium hydride can trigger an intramolecular SN2 reaction, resulting in the formation of a cyclic ether. Typically, these reactions favor the formation of 5- and 6-membered rings as they have minimal ring strain. In contrast, 3- and 4-membered cyclic ethers are less likely to form due to the significant ring strain associated with smaller ring sizes. These ethers, along with other methyl, primary, or secondary ethers, can be cleaved by reacting with a strong acid that provides a nucleophilic conjugate base, such as hydrogen iodide. The non-bonding pair of electrons on the oxygen atom of the ether attacks the acidic proton in an acid-base reaction, resulting in the formation of a protonated ether and a free iodide anion. The nucleophilic iodide anion then attacks the alpha carbon bonded to the protonated ether, causing the neutral alcohol to leave as a good leaving group. For non-cyclic ethers, this reaction produces 2 separate products, an alcohol and an alkyl iodide. In contrast, for cyclic ethers, the nucleophilic attack results in a single product containing both the alcohol and the halide. At this point, you may be wondering how we synthesize tertiary ethers. Unfortunately, the Williamson ether synthesis does not work for this purpose. SN2 reactions at tertiary substrates are hindered by steric bulk and instead lead to E2 elimination due to the strong basicity of the alkoxide nucleophile. Instead, we can employ the SN1 mechanism to form more substituted ethers. In this reaction, the leaving group departs from the substrate, resulting in the formation of a tertiary carbocation intermediate. Provided this carbocation is stable and does not undergo rapid rearrangement, it can then be attacked by the oxygen of an alcohol in a Lewis acid-base reaction to form a protonated ether intermediate. Subsequent deprotonation yields the ether product. We can leverage the property of ethers as protecting groups for alcohols in Grignard reactions. Recall that Grignard reagents are strong nucleophiles and also very strong bases. If alcohols are left unprotected, their acidic protons are rapidly deprotonated by the Grignard reagent, preventing the desired nucleophilic attack on the electrophile. By converting the alcohol into an ether, we effectively protect the alcohol, allowing the Grignard reagent to react selectively with the intended electrophile. Consider the ketone we plan to use in the following reaction. First, we observe that the molecule containing the electrophile in this Grignard reaction also has an alcohol group with an acidic proton. To prevent this proton from interfering with the reaction, we can protect the alcohol. This is achieved by treating the molecule with tert-butanol, catalytic sulfuric acid, and sodium sulfate. This protection step converts the alcohol into a tert-butyl ether, shielding it from subsequent reaction with the Grignard reagent. Let's break down the mechanism for acid-catalyzed ether synthesis using tertiary alcohols. In the first step, the hydroxyl group of the tertiary alcohol, such as tert-butanol, uses a lone pair of electrons to deprotonate the acidic proton from sulfuric acid H2SO4 in an acid-base reaction. This generates an oxonium ion, which is an excellent leaving group. The oxonium ion then departs from the tertiary substrate, forming a stable tertiary carbocation and water as a byproduct. However, as long as water is present, the reaction exists in equilibrium and is easily reversible because water, although a poor nucleophile, can attack the carbocation, reforming the tertiary oxonium ion. To drive the reaction forward, the water must be removed. This is achieved by adding sodium sulfate, Na2SO4, a drying agent that absorbs water and forms a hydrated complex with the formula Na2SO4H2OX, where X represents the number of water molecules. Once the water is removed, the tertiary carbocation remains as a highly electrophilic intermediate. This carbocation is then attacked by the hydroxyl group of the primary alcohol from the starting material. The lone pair of electrons on the hydroxyl group of the primary alcohol performs a nucleophilic attack on the carbocation. The resulting intermediate is then deprotonated by the conjugate base of sulfuric acid, regenerating the catalytic H2SO4 and forming the final protected ether product. To cleave a tertiary ether back into the original alcohol, we simply add an acid, such as H3O+. The aqueous acid protonates the oxygen atom of the tertiary ether, converting it into an excellent leaving group, much like an oxonium ion. This allows the ether bond to break, releasing the alcohol from the tertiary substrate. The reaction then relies on the large abundance of water in the system to establish equilibrium between the tertiary carbocation and the tertiary oxonium ion, ultimately regenerating the original unprotected alcohol. This cleavage step naturally complements Grignard reactions, which end with an acid workup. As always, let's do some practice. Propose reaction sequences to accomplish the following transformation. Specify necessary reaction conditions and reagents. You may use any building block with less than or equal to 2 carbons for your syntheses. However, the reagents that you use that are not incorporated into the final product may contain more than 2 carbon atoms. The structure of the reactant and the product should be shown for each chemical transformation. Feel free to pause the video and try these problems on your own first. In the first reaction, we are tasked with proposing a series of steps to transform the starting material into methylphenidate. To determine the required steps, we can use retrosynthetic analysis, working backward from the product to identify the intermediates and reactions needed to complete the transformation. First, we observe that the product contains 2 more carbons than the starting material. Additionally, the product involves the formation of both a carbon-carbon bond and a carbon-oxygen bond. Taking one step back from the product, we recognize that the methyl ester group could be derived from a carboxylic acid. The carbon of this carboxylic acid corresponds to the site where the carbon-carbon bond forms. To generate the carboxylic acid, we can start with a Grignard reagent, which reacts with carbon dioxide to produce the acid. This suggests that we need to first convert the starting material into a secondary bromide and then prepare the corresponding Grignard reagent. Working further backward, we know that secondary bromides can be synthesized from secondary alcohols, which, in turn, can be formed from the reduction of the starting ketone. This chain of transformations connects the product back to the starting ketone, giving us a clear sequence of steps to achieve the desired synthesis. In the first step, the ketone is reduced to form the corresponding secondary alcohol. This reduction can be achieved using a reducing agent such as sodium borohydride, NaBH4 in ethanol, followed by an acid workup, or lithium aluminum hydride, LiAlH4 in diethyl ether, also followed by an acid workup. Next, the secondary alcohol is converted into a secondary bromide. This transformation can be accomplished in one step by treating the alcohol with phosphorus tribromide, PBr₃. The secondary bromide is then converted into a Grignard reagent by reacting it with magnesium in diethyl ether. This Grignard reagent is subsequently used to form a carboxylic acid by reacting with carbon dioxide, CO2, which acts as the electrophile. Finally, the carboxylic acid is deprotonated to form a carboxylate anion, which serves as a good nucleophile. The carboxylate anion then reacts with methyl iodide CH3I in dimethyl sulfoxide, DMSO, resulting in the formation of the desired methyl ester product, completing the synthesis. In the second reaction, we are tasked with transforming the starting material, 2-bromophenol, into salicylic acid. Using retrosynthetic analysis, we can work backward from the product to identify the necessary steps. The product contains a new carbon-carbon bond, which can be formed by reacting a Grignard reagent with carbon dioxide. This suggests that the product is just one synthetic step removed from the Grignard reagent, with the starting material serving as the precursor for its formation. However, the acidic proton on the phenol in the starting material presents a challenge. If the phenol were directly converted into a Grignard reagent, the acidic proton would react with the reagent itself in an acid-base reaction, neutralizing it and preventing the desired transformation. Therefore, the phenol group must first be protected to enable successful Grignard formation. To address this, the synthesis begins with protecting the phenolic alcohol by reacting it with tert-butanol in the presence of catalytic sulfuric acid and sodium sulfate, forming a tert-butyl ether. This protects the phenol's acidic proton while leaving the aryl bromide available for further reactions. Next, the aryl bromide is converted into a Grignard reagent using magnesium in diethyl ether. The resulting Grignard reagent is then reacted with carbon dioxide, CO2, to form a carboxylic acid. During the acidic workup, the magnesium-oxygen bond in the Grignard carboxylation intermediate is cleaved to release the carboxylic acid. Simultaneously, the acidic conditions also hydrolyze the tert-butyl ether, regenerating the phenol group. This sequence produces salicylic acid as the final product. By addressing the challenges posed by the phenol's reactivity and carefully protecting and deprotecting the alcohol group, we achieve the efficient transformation of 2-bromophenol into salicylic acid. As always, thank you for watching, and I'll see you next time.